Hi everyone. Now we are going to discuss with Unit 3 Significant Figures. The objectives of these units: significant figures, and rules to determine significant figures, calculations involving significant figures, confidence limits, correlation coefficient, and regression analysis. Significant figures, it represents the analytical data obtained from the measurement. Certain figures which involve the number of digits are necessary. The figures used to estimate the uncertainty involved in the measurements are called significant figures. The definitions of significant figures is very simple. The significant figure is a number may be defined as all certain digits plus one doubtful digit. For example, in that trigonometric analysis, if the volume of the liquid is measured by a burette which is graduated to 0.1 ml, any volume reported should reflect this. For example, volume of 12.6 ml and volume of 12.60 ml are numerically the same. But from the analytical report or analytical point of the 12.6 ml containing three figures is significant when burette is graduated to 0.1 ml, whereas actual volume is 12.6 plus or minus 0.1. 12.6 ml containing four figures is significant if burette is graduated to 0.01 ml. In the above example, the number 1 and 2 are known with certainty, while there is some uncertainty in the last digits, so that the actual volume would be anything between 12.5 and 12.7 milliliter. On the other hand, reading of 12.6 ml implies that the actual volume could be anything between 12.59 and 12.61 when burette is graduated to 0.01 ml. That is, the actual volume is 12.6 plus or minus 0.01. Non-zero integer. The term non-zero integers are significant. For example, 5.251 has four significant figures. 2.45 has three significant figures, and 6.251 have five significant figures. Here there is no any zero term is present, hence that is non-zero integer. Recognition of errors in significant figures. The digit 0 may or may not be significant figures. If the burette graduated to 0.01 ml, let the burette reading 20.05 ml. This contains four significant figures. Here both zeros are treated as significant figures because the zeros present is in between two non-zero digits. If the above burette reading is expressed in liter, it could be 0.0025 later. Since the number of significant figures cannot change just by changing the unit, this number should have only 4 significant figures. The function of 0 precedings is only to locate the decimal point, hence that initial zeros are not significant. Similarly, a volume of 2 liters expressed in ml. Consider that examples like a 2000 ml must contain only 1 significant figures, which is what true. To avoid this ambiguity, it is safe to express the number in powers of 10. Thus, 2 liters should be written as a 2 into 10 to the power of 2 into 10 to the power of 5 ml. Here, having only 1 significance. If, however, the volume expressed in liter is 2.1, the volume in milliliter will be 2.1 into 10 to the power of 5. What it means? Here, before multiplicity, how many digits are there? That is considered as that significant figures. The following example, it is clearly illustrated. The points mentioned. The number is 0.612. The expression is 612 into 10 to the power of minus 3. Here, 3 significant figures. Here, 0 is not significant here because there is no any 0 term. 70.9. That is expressed here. 709 into 10 to the power of minus 1. Here, 3 significant figures. 0 significant figures present. Here, 0 is present before that and after, or 0 is in between 2 non-zero digits. That is considered as a false significant. Here, 0.007. That is expressed in that. 7 into 10 to the power of minus 3. Here, having only 1 significant. Here, zeros are not significant figures here. 6.02 into 3 into 10 to the power of 23. This is scientific notation or Avogadro's values. In that Avogadro's values, we are considered all are significant. Here, 4 is the significant. Here, 0 is significant figures here. Here, 1.03 into 10 to the power of minus 3. Here, 3 is the significant figures. First, we consider what is that leading zeros. The leading zeros means zeros that precede all the non-zero digits are called leading zeros. These are not counted as significant figures. They merely indicates the position of decimal point. For example, 0.007, the zeros are leading to 0, so that there 0.007 has only 1 significant figures. Captive zeros. Captive zeros means zeros between 2 non-zero digits are called captive zeros. These are always counted as significant figures. For example, 70.9, 0 is the captive zero and thus it is taken as significant figures. Therefore, 70.9 has 3 significant figures. Similarly, 5.02 has 3 significant figures. Trailing zeros. The zeros at the right end of the number are called trailing zeros. They are significant if the number contains decimal point. Thus, N900.00. Zeros are the examples of trailing zero or significant as these are present after the decimal point. When the number ends in zeros that are not to right of the decimal point, the zeros are not necessarily significant. For example, the number 240 can have 2 or 3 significant figures. Similarly, 20500 can have 3, 4 and 5 significant figures. Next, the term introduced exponential notation. In exponential notation, the numerical portions represents the number of significant figures. For example, 5 into 10 to the power of 6 as having only one significant figure. 5.2 into 10 to the power of minus 4. It has two significant figures. How to rounding of the non-significant figure? The non-significant figures in the measurement are rounded off as per the following rules. If the digits following last significant figure is greater than 5, the number is rounding of the next higher digit. For example, 9.48 can be rounding off 9.5. If it is less than 5, the number is rounded off the present value and the last significant figures. Consider 9.42 is rounding off to 9.4. If the last digit is 5, the number is rounded off to the nearest even digit. For example, 8.65 is rounded off to 8.6, 8.75 is rounded off to 8.8, 8.55 can be rounded off to 8.61. The following rules are to be followed while doing calculations involving significant figures. What are the rules are following here? All non-zero digits are significant. Consider all non-zero digits are significant. 1.234 has 4 significant. Here 1.2 has 2 significant figures. Zeros between two non-zero digits are significant. Here 1002 kg has 4 significant figures. Here zeros present is in between two non-zero digits as 4 significant figures. 3.07 ml as 3 significant figures. Zeros to the right left of the first non-zero digits are not significant, such zeros nearly indicate the positions of the decimal point. Consider 0.001 degree Celsius as having only one significant figure, 0.012 gram as 2 significant figures. Zeros to the right of a decimal point in a number are significant. 0.23 has 2 significant figures. 0.200 gram has 3 significant figures. When number ends in zeros that are not to right of a decimal point, that zeros are not necessarily significant. 190 miles may be 2 or 3 significant figures. 50.600 calories may be 3, 4 or 5 significant figures. The potential ambiguity in the last rule can be avoided by the use of standard exponential, that is what scientific notation. The scientific notation is always expressed in the terms of n into 10 to the power of n form. Here, capital N is from 1 to 9. Consider here 5600 calories is expressed in that 5.06 into 10 to the power of 4. Here, having only 3 significant figures, here 4 significant figures, here 5 significant figures. The exact number. Some numbers are exact because they are known with complete certainty. Most exact numbers are integers. Exactly 12 inches are in a foot. There might be exactly 23 students in a class. Exact numbers are often found as conversion factors as count of an object. Exact numbers can be considered to have an infinite number of significant figures. Thus, the number of apparent significant figures in any exact number can be ignored as a limiting factors in determining the number of significant figures in the result of calculations. Rules for mathematical operations. Here certain rules were followed to mathematical operation in additions and subtractions, multiplications and divisions. Here the result is rounded off to the last common digit occurring further to the right in all components. For example, 100. 100 significant figures 3. 23.643. Here significant figures 5. Just we are going to add which should be rounded off to. Here 100. 23.643. Just we are going to rounding off 123.643. Here this is expressed in that significant figures 3. How to express it in that significant figures 3 here? Here 6 is greater than 5. 6 is greater than 5. That's why the term is written as 124. Here significant figures is 3 ohm. In multiplication and divisions, the result should be rounded off so has to have the same number of significant figures as in the component with the least number of significant figures. Consider significant figures like 3. Here 2 is the significant figures, 12.60, 4 is the significant figures. We are going to multiply what we are getting 37.8. We should be rounding off to 38 because in that least significant figures of this number is 2. Rules for rounding of numbers. If the digit to be dropped is greater than 5, the last retained digit is increased by 1. Yet 12.6 is rounded to be 13. If the digit to be dropped is less than 5, the last remaining digit is left as it is. For example, 12.4 is rounded to 12. If the digit to be dropped is 5, if any digit following it is not zeros, the last remaining digit is increased by 1. Yet 12.51 is there, that is expressed in that 30. If the digits to be dropped to 5 is followed by any zeros, the last remaining digit is increased by 1 of it is off, but left as it is even. Here 11.5 rounded to 12, 12.5 rounded to 12. This rule means that if the digits is to be dropped to 5 followed only by zeros, the result is always rounded to the even digit. The rationale is to avoid bias in rounding. Of the time we round up, half the time we round down. What are the general guidelines for that using calculators? When using a calculator, if you work the entirely of a long calculations without writing down any intermediate results, you may not be able to tell if an error is made, even if you realize that one has occurred. You may not be able to tell where the error is. In long calculations involving mixing operations, carry as many digits as possible through the entire set of calculations and then round the final results appropriately. For example, 5 divide 1.235 plus 3 plus 6.35 divide 4. What we are getting here? 8.630892. The first division should result in 3 significant figures. The last division should result in 2 significant figures. The 3 numbers added together should result in a number that is rounded off to the last common significant digit occurring furthest to the right. The correct rounded final results should be 8.6. This result has been limited by the accuracy in the last division. Here, rules for calculations involving significant figures. Already it is over. Rules for logarithm and anti-logarithm. Logarithm is composed of 2 parts, such as a whole number called characteristics and decimal fractions are called mantissa. The characteristics is a function of positions of the decimal in the number of whole logarithm is being determined and therefore is not a significant figure. The mantissa is the same regardless of the position of the decimal point and all the digits are considered significant. For example, consider the logarithm 2.5 into 10 to the power of 5. The characteristics is 5. The characteristics is 5. Using the table, mantissa is rounding of that 0.561. Since the number is 2s has 2 significant figures, if mantissa should contain only the same number of significant figures, hence mantissa can be expressed as 0.56. While taking anti-logarithm, result should contain the same number of significant figures at this mantissa. Thus, anti-log of 1.946 is 99.5 as its mantissa is 0.946 contain 3 significant figures. This antilog should also contain the same number of significant figures, that is 3. Confidence limit. The confidence limits means the boundaries of this range is called what? The confidence limits. The likelihood that the true value fall within the range is called the probability or confidence level, and that is often expressed as a percentage. Consider the example that in a set of iron determinations it is 95% probable, that is the pollutions means mu lies in the limit plus or minus 0.2% iron of the sample mean 11.30% iron. It tells that the confidence interval is 11.10% to 11.50% iron with 95% of this probability. 95% confidence limit for mu is equal to 11.30 plus or minus 0.20% iron, and this confidence level is 95%. The confidence interval when sigma is known or S is a good estimate of that sigma. We consider that normal error curve can be expressed in that equation. Here, y sigma is equal to x minus mu. In that single variable, y is defined as x minus mu by sigma. For the definitions of why it is followed, that is x minus mu is equal to plus or minus y mu. This is the mathematical expressions to find the confidence level when sigma is known or S is a known. Here, these are all the terms to measure that confidence level corresponding to the y value. The confidence intervals for mu is equal to x bar minus x bar plus or minus y into sigma by root n. That is also rewritten as x bar minus y into sigma by root n or x bar plus y sigma by root n. By using these expressions, we are going to calculate the confidence level. Some values they are provided. Some y values provided. What is that y value? 1.96 for first example. In that 99% confidence level, we are giving 2.58. Just we are going to substitute all the values into that equations. What we are getting, that confidence level. The confidence interval when sigma is not known. That time we are using this formula. When sigma value not known, that time t is equal to plus or minus x bar minus mu by s by root n. That equation is also modified that x bar minus mu into root n by s. The statistician have says that the values of t for given degrees of freedom, here mu is equal to n minus 1 and for various confidence level is desired. Some statistical persons says that, they provide that some t values, here mu value variations, a 90% confidence level and 95% and 99% confidence level with respect to degrees of freedom they mentioned here. A simpler and approximate procedure particularly useful for small numbers of observations, that is expressed in terms of n. To express confidence interval is based on the range R. R means the difference between the largest and smallest values of observation. According to these, to a certain degrees of confidence, populations means mu lies within the limits. Here mu is equal to x bar plus Cn into R. Here Cn is constant depending upon the number of observations and the desired confidence level. A few values of C are tabulated in that table. To summarize that units, the scientific measurements are reported to say that every digit is certain except the lost, which is estimated. All digits of measured quantity, including the certain one, are called significant figures. There are conventions that must be followed for expressing numbers so that their significant figures are properly indicated. These conventions, all non-zero numbers are always significant. All zeros between non-zero numbers are always significant. All zeros which are simultaneously to the right of the decimal point and at the end of the number is always significant. All zeros which are to the left of a written decimal point and or number greater than or equal to 10 are always significant. Thank you.